All right, so this is part 2 of our solving using squares. And make sure again that you've already completed the first video. And just to highlight a couple things in the first video is we're looking at our last term, if you would, to see if it's a perfect square. And if we identify a perfect square, we want to then look to see if the b term is twice that square root. And that happened in both of our first examples here. But now let's take a look at our new examples. And something that you should see in our new examples is not only do we have a perfect square as our c value, but you can see that now our a value is also a perfect square. So we can still look to see if these are perfect squares. And so how we do this is going to be as follows. I'm mentally looking here at this 9. And I know the square root of 9 is 3. Square root of 4 is 2. And so now what I'm looking at is 2 times 3 is 6. And there's that doubling scenario. I see that 12 is twice as large as 6. So now this is telling me this is that perfect square. So what I'm capable of doing in this case is I can take this problem and factor it. It's going to be 2x minus 3 squared. And then obviously I'll leave it equal to 16. So now this is great for me because now, since I identified that special pattern, I can now solve this by inverse operations. If I continue working this problem out, I take the square root of both sides. That gives me 2x minus 3. Don't forget the plus or minus. And now let's continue working this out. 2x, 3 plus or minus 4. So this is a good place to actually say 3 plus 4 is 7. 3 minus 4 is negative 1. So then that's going to tell me I have a 2x is equal to 7 or it's equal to negative 1. So I have x equals 7 halves or negative 1 half. So now you can see had a little bit messier of a problem. And again, a lot of that stems from the fact that our leading coefficient is now no longer 1. It's some other number, and it's another perfect square, which is 4. I understand there's a couple extra steps in there, but see if you can't now pause the video and attempt number 4 here based off of how I did number 3. Again, I'm going to move forward as if you've already had a chance to try this. And one of the things, again, you'll see is 9's a perfect square, 25's a perfect square. Square root of 9 is 3. Square root of 25 is 5. 3 times 5 is 15. Times 2 gives us the 30. There's our perfect square. So now that's going to enable me to write this as 3x. And again, I see that I'm trying to get a negative, so I'm going to put minus square root of 25 is 5. Right side stays the same. Now again, this takes us right to our favorite part. We have parentheses being squared. See parentheses being squared? I'm going to take the square root of both sides. Now I have 3x minus 5 equals plus or minus square root of 10. At first, I'm thinking, square root of 10, but just leave it to square root of 10. Don't use a decimal approximation or anything like that. There's no perfect squares that go as a factor of 10. So I'm going to continue solving this by adding 5 to both sides. And then finally, I'm going to divide both sides by 3. And it looks messy, but right there it is. There's our final answer. 5 plus or minus the square root of 10 over 3. So in conclusion, what we're going to be looking for in all these problems are our perfect squares. And if we see perfect squares as our leading coefficient and our ending constant, then we have a little bit of a red flag that goes off in our head. And we're going to check to see if their square roots can be multiplied together times 2 to give us that middle number. If so, we can rewrite it as a square and then use inverse operations to solve.